So let's put what we know together. We know that if we want to graph a function like secant or cosecant, we have to deal with their reciprocals, which would be sine or cosine as appropriate. And in this case, y equals 2 secant of 3x will be very similar to y equals 2 cosine of 3x. So if we know what happens with cosine of 3x, 2 cosine of 3x, we know what happens here. So let's use that as a guide. Here's the way I'm thinking about it. Let's just examine what the function, examine, that's supposed to say examine, y equals 2 cosine of 3x would look like. And we'll just do it through at least one cycle, and then if we have more room, we'll put in more cycles so that we can see it. Well, this is a function that would have an amplitude of 2 and would have a period of 2 pi over 3 and would have key points located at pi over 6 apart. Right, so if I'm graphing cosine 2 cosine of 3x, the easiest way to deal with it, let's see, x, our key points here, y, we would have within one cycle starting at 0, key points that are pi over 6 apart, so 1 pi over 6, 2 pi over 6, 3 pi over 6, and 2 pi, or say 4 pi over 6, which becomes 2 pi over 3, right? These are key points that are one cycle apart. So what could we say here? In this case, y would be for cosine 2, 0, negative 2, 0, and 2. All right. So if I'm graphing that, here's how that should look on my cycle. Here's 1, here's 2, here's 3, here's 4. I'm going to label my axes because it helps me to see what's going on. 5 and then 6. And of course going in the negative direction, negative 1, negative 2 here, negative 3, negative 4 here, negative 6 here. And then along the horizontal axis, let's mark off our key points by pi over 6. So here's pi over 6. Here's pi over 3. Here's pi over 2. Here's 2 pi over 3. And then we're just going to keep on going right here. So we'd have 5 pi over 6 would be the next key point. Here would be pi. This last guy over here would be 7 pi over 6. And here's 0 back here. Here's negative pi over 6 just for comparison's sake. Okay, so labeling all that out. What do we do here? Well, let's see. In purple, our graph is going to go 2, 0, negative 2, 0, and 2. And if we keep following this pattern, we go back to 0, negative 2, and 0. To the left here would be at 0 at negative pi over 6. We know what's going to happen right here. I don't really even need to graph in the entire cosine function to follow the bouncing balls, as it were. Right? What I could do is I could just say, well, where will my vertical asymptotes occur? I know that if I'm talking about the secant of function, 2 secant of 3x, my vertical asymptotes are going to occur everywhere where 2 cosine of 3x was equal to 0. So I'm going to get a vertical asymptote at pi over 6. I also know I'm going to get a vertical asymptote at pi over 2. And 5 pi over 6 would be next, right? Because that's where it's crossing the x-axis. 7 pi over 6 would be next after that. Kind of interesting how this is going. We don't even have one here at negative pi over 6. And if we wanted to draw the graph, we know that what's going to happen is that each of our branches of this secant function are going to have the reciprocal behavior of the cosine branches. So instead of going down towards 0, it goes up towards positive infinity. Or instead of going towards 0 between these two, it'll go towards negative infinity while passing through negative 2 here at pi over 3. Right, so we're going to get 2. We're going to get negative 2 here. We're going to get 2 here. And then the rest of the graph follows. All right. Now, one thing that we would probably be asked to do is identify the locations of the vertical asymptotes or to find our domain. And I'll show you how we can do that rather easily here with a secant or cosecant. All right. Remember that if it were just y equals cosine of x, right, we said that we would have asymptotes at odd multiples of pi over 2. So 2n plus 1 multiples of pi over 2. Right? The only difference is that in this case, instead of having cosine of x, we actually have secant of 3x. So in order to isolate x right here, vertical asymptotes are going to be at wherever x is equal to 1/3 of both sides. And that's like saying 2n plus 1 times 1/3 of pi over 2, so pi over 6. Now we might ask, well, how is that working out according to our asymptotes? Well, let's just check. If n is equal to 0, then x equals 2 times 0 plus 1 times pi over 6, pi over 6. Yep, that's a vertical asymptote, all right. At n equals 1, what happens? Well, we've got 2 times 1 plus 1, that's 3 pi over 6. 3 pi over 6, which one is that? Oh, wait a minute, that reduces, doesn't it? Right? It's pi over 2. That's a vertical asymptote, all right. Let's try n equals 2. At n equals 2, we're going to get 2 times 2 plus 1, that's 5. That gives us 5 pi over 6. Sure enough, 5 pi over 6 is another of our vertical asymptotes. And so we can see that this formula works. That gives us the location of our vertical asymptotes. And by the way, our domain for the function is going to be the set of all values of x such that x does not equal odd multiples of pi over 6, 2n plus 1 multiples of pi over 6. And for our range, right, for the cosine range here in this function stayed between -2 and +2, so our reciprocal range for the cosecant will be -infinity to -2, union with a set from 2 to +infinity. So this is how we can quickly generate a graph of a secant. It's similar, by the way, it would work the same thing for cosecant by using either the sine or cosine function to help guide it.